Hello again. One thing that we did not discuss in the previous lecture was what happens to a block state when I operate on it by the momentum operator. The momentum operator is h cross upon I grad, and the block state is e to the I k dot r uk of r. And what this gives me is the following. This gives me h cross k plus h cross over I del times del operating upon un, or I don't need the band index, so I'll just give the ordinary uk of r, or that's equal to h cross into k plus p operating on uk of r, and this is the one that gives rise to k dot p perturbation theory that we discussed before. Now let me introduce an operator that you are already familiar with, which is actually the lattice translation operator. So if I introduce a lattice translation operator, which I call Tn is the lattice translation operator defined as follows. So Tn operating upon a function f of r will give me f of r plus Rn, where Rn is the lattice translation, is a lattice translation vector. Now we know from quantum mechanics that the rate of change of the expectation value of any operator A. So supposing I give you an operator A, the rate of change of the expectation value of A in any state psi is actually given by IH cross d by dt A is equal to expectation value of the commutator A comma H, where H is a Hamiltonian. Now what we will do is we shall apply a force on the system given by F equal to minus Fx I minus Fx j, minus Fyj minus Fz k. Since force is always a gradient of some potential, the potential corresponding to this force is the following. This force is U equal to, let me keep them plus because I am going to put the minus in the potential. U is equal to minus Fx x minus Fy y minus Fz z, where x, y, z are the components. Now supposing I want to find out what happens to the variation of this expectation value of the lattice translation operator. That is, I want to find out the time variation of the expectation value of the lattice translation operator Tn. This is given by Tn comma h naught, h crystal minus fxx minus fyy minus fz z, because this part that I have here is the potential u that I have added to that to impart a force F that is given here. Now we know that Tn comma H crystal is equal to 0. So what we can write down is IH cross d by dt Tn is equal to Tn comma minus fxx minus fyy minus fzz, or that is simply equal to minus fx x plus r n x, sorry, there is no r n x is simply the x component of the translation vector. X goes into this one, so let me, in order to avoid any confusion, let me write fx later minus of into f of x minus y plus r n y into f y minus z plus r n z into f z times Tn, because this is what the Tn commutator means, and then I have minus xfx minus of minus xfx minus yfy minus zfz times Tn. Or I can simplify it. I can just say that it is nothing but minus rnx fx minus rny fy minus rnz fz times Tn, because you will see that xfx cancels against xfx and so on and so forth. So this is what I will get. Now there is one more thing that we should know at this point, that is Tn is commuting, Tn commutes with H naught. Hence H crystal actually hence e to the ik dot r ukr is also an eigenstate of Tn. So what is the eigenvalue? So that is, let me call it psi of k equal to . So Tn psi of r is equal to lambda k psi k of r, but by Bloch's theorem we also have this is equal to e to the ik dot rn psi k of r, because this is actually equal to psi k r plus rn. So the Bloch's theorem says that any translation operator says that any translation Tn psi k of r should give me this state, and it's Bloch's theorem says that this state must be equal to this state, that is psi k r plus rn is equal to e to the power ik dot rn psi k of r. Therefore lambda k is equal to e to the I k dot Rn. So we want to take the find out what the rate of change of the expectation value of Tn is. So I want to find out what is IH cross d by dt Tn is. So this is equal to IH cross d by dt of e to the I k dot Rn is equal to h cross d by dt k times e to the I k dot Rn. It is just a straightforward differentiation, k as a function of time. Now the other one that I have is the right hand side of the above equation, that we have here, this one. Right hand side of that will give me the following, that is expectation value of Tn multiplied by minus fx Rnx. This also has a Rn, sorry, just a second, let me just correct it. I also have h cross Rn dot that one. Okay, so this is minus f of x times Rnx minus f of y times Rny minus f of z times Rnz. The right hand side of that one is actually given by the following, times e to the I k dot Rn, because e to the I k dot Rn is the expectation value of Tn. Since Tn is equal to e to the power I k dot Rn. So what it means is I can cancel out e to the I k dot Rn. So what I have is h cross times dkx by dt Rnx plus dky by dt Rny plus dkz by dt Rnz is equal to minus fx Rnx minus plus fy Rny plus fz Rnz. Now equating them by components, what we get is the following. If I equate them by components, I will see that h cross dk by dt is equal to f external. So with this, what you see is very interesting, that is h cross k behaves like the momentum of the wave packet. Psi k. So and this thing, so what will happen is that h cross dk by dt will be the group velocity of the wave packet. Sorry, h cross k is not h cross dk by dt. H cross k by m is equal to the group velocity of the wave packet and dvg by dt will give you the force. because dvg by dt is the acceleration of the particle. So this is something that we already used it. We had already used it while discussing effective mass concept. We have a better idea just to summarize this part. So what we know is that the wave vector k of the Bloch state does not is not giving you the momentum of the electron, but h cross k actually gives you the h cross k by m actually gives you the group velocity of the wave packet that is formed by the superposition of these site orbitals using the phases e to the power I k dot r n. Well, now having done this, I want to go into a slightly different topic, which is basically the symmetries, non-spatial symmetries in the Hamiltonian. The spatial symmetries in the Hamiltonian gave you the group of the wave vector, and also showed you how you can have only need to work with a particular part of the Brillouin zone, and how you can actually connect up the states E versus k states when you move from one symmetry point in the Brillouin zone to another symmetry point in the Brillouin zone as you go along in your band structures. That was a BSW notation, that is the Brillouin, Boucard, Smoluchowski and Wigner notation. Now let me look at other symmetries. So these are the non-spatial symmetries in the Hamiltonian. One of the non-spatial symmetry, the only non-spatial symmetry in fact that I am going to be dealing with, is the time reversal symmetry. So what is time reversal symmetry? In classical systems it is defined like this. In classical systems, the system has time reversal invariance if at a time t naught we reverse all the momentum and the system retraces its classical path. For example, supposing I have a system whose trajectory is the following. Okay, the trajectory starting with time 0, I go to time t naught. Now at time t naught, what I will do is I will reverse all the momenta in the system. When I reverse all the momenta in the system, if the system retraces its path, then I say that the system has got time reversal symmetry. So this system will have time reversal invariance. The example of a system without time reversal invariance is a moving charged particle in a magnetic field. Consider a charged particle moving in a magnetic field. The trajectory, let us say, is the following. I have started from 0 and the trajectory is, this is t naught. Now if I reverse the reverse all the momenta retaining the magnetic field, then what happens is this particle starts moving in a different direction. So this is the case where the system does not have time reversal invariance. So now for time reversal we can always define an operator for time reversal is T. Then if a Hamiltonian is invariant under time reversal, then TH T dagger is equal to T, or TH equal to HT. Now we know that when we time reverse, the momentum changes sign, but the position does not change sign. So what it means is that TP T dagger, but time reversal transformation changes the momentum. So momentum from P to minus P. So this means that we must have TP T dagger is equal to minus P, or TP is equal to minus PT. But it does not change the position operator. The position operator is unaffected by time reversal operation. That means TR is equal to plus RT, or T or T dagger is equal to R. So this, the fact that P goes to minus P under time reversal implies that T can be written as T equal to U times K. U is a unitary operator, and K is an operator which takes a complex conjugate for complex conjugation. So that must be the form of the time reversal operator. Now what we have is, since T commutes with H, T psi is also an eigenstate of H. That is, what we have is the following: TH is equal to HT, therefore T psi is equal to some eigenvalue, let me call it T, is not important at this point, is equal to T psi, and T psi is also an eigenvalue, that is T psi is an eigenstate of H if psi is an eigenstate of H. If psi is an eigenstate of H. Now let me take the time dependent Schrodinger equation and operate by t. So what do I get? I will have IH cross d by dt psi of r comma t is equal to H psi r comma t. So when I operate by t on both sides, then what I have is t operating on IH cross del psi by del r t will give me minus IH cross, because there is a complex conjugation, and then d by dt, okay, and since it is a time reversal I can write it as r comma minus t, t goes to minus t, and you can also look at it this way, t goes to minus t, so IH cross goes to minus IH cross, because d by dt becomes minus d by dt. So this is equal to H t psi r comma t. Now let us look at it more carefully. Supposing I have IH cross d psi by dt is equal to H psi, then if I take complex conjugates on both sides, H is real, the Hamiltonian is real, because of that I have minus IH cross d psi star by dt is equal to H psi star. If we take complex conjugate on both sides. Now compare this equation with this equation. So what it means is that because t psi r comma t is also an eigenstate, what we have is that psi of r minus t, so this actually goes to psi of r minus t. So what it means is that psi of r minus t is equal to psi star r comma t. So this is one of the properties. So the property that I talked about is that t is equal to uk and t psi is an eigenstate with same eigenvalue with same energy eigenvalue as psi. For this all you need to do is take a particular linear combination of psi's for degenerate states where they are also eigenstates of psi t. So you can do this, and psi of r minus r comma minus t is equal to psi star r comma t. So these are some of the general results that we got, and now let us see how we can obtain operators, operator t for spatial operation as well as on spins. This we shall discuss in the next lecture. This is a convenient point to stop. So let me stop at this, and we will proceed with the next lecture on the same topic. Thank you.